Hello, my name is Kaylin Maher. The title of my video is Free Energy in Thermodynamics, Solving for the Number of Microstates in a Given System. I will be solving problem set number 7, 1A and C. The problem asks, how many microstates are in the following systems? A molecule of hydrogen gas and 5 molecules of chlorine gas. A microstate is defined as a unique arrangement of molecules or particles. In other words, each snapshot of a molecule in one particular moment is one microstate. To solve this problem, we use Boltzmann's equation. Boltzmann theorized that the entropy of a system was related to the number of different ways particles could be arranged. Boltzmann's equation is written here. S equals Kb ln W, where S is the entropy in joules per Kelvin, W is the number of microstates, Kb is 1.381 times 10 to the negative 23rd joules per Kelvin, or Boltzmann's constant, and Kb can be obtained from R divided by Na, where R is equal to 8.314 joules per Kelvin, and Na is Avogadro's number 6.022 times 10 to the 23rd. We begin by isolating W, or the number of microstates, because the problem asks us to solve for the number of microstates. To solve for W, we begin by dividing S by Kb. We use E on both sides of the equation in order to cancel out the natural log. We are then left with the equation E raised to the S divided by Kb power is equal to W. Now, we can obtain the value of S, or entropy, from the appendix of the textbook. S of hydrogen gas is equal to 130.7 joules per mole Kelvin. To find S for one molecule, we multiply our S value by 1 mole divided by 6.022 times 10 to the 23rd molecule. We do this step because the problem specifically asks for the number of microstates in one molecule of hydrogen gas. This gives us the value of S for one molecule, which is equal to 2.170 times 10 to the negative 22nd joules per Kelvin. Finally, we plug in this S value that we just obtained and Boltzmann's constant into the equation where we isolated W. This gives us a value of 6.689 times 10 to the 6 microstates per hydrogen gas molecule. We use 4 significant figures in our answer because our S value obtained from the back of the textbook limits us to 4 significant figures. We can use the same equation, S equals Kb ln W, for problem 1C. We also can begin by isolating W, which is done on the left side of the screen and was shown previously. The S value, 223.1 joules per mole Kelvin, is obtained from the back of the textbook. We follow a similar set of steps in problem 1C. We begin by multiplying our entropy, 223.1 joules per mole Kelvin, times 1 mole divided by 6.022 times 10 to the 23rd molecules. However, because 1C asks us for the number of microstates in 5 molecules of chlorine gas, we multiply this value by 5 instead. This gives us an S value of 1.852 times 10 to the negative 21 joules per Kelvin. Similar to the previous problem, we plug our S value into the equation on the left, as well as Boltzmann's constant. This gives us a W value of 1.791 times 10 to the 58th microstates per 5 chlorine gas molecules. We also use 4 significant figures for this problem because our S value, once again, limits us to 4 significant figures. To summarize, the problem asks for the number of microstates in a given system. A microstate is a unique arrangement of molecules or particles. To solve for the microstates, we used Boltzmann's equation and isolated W. Then, we plugged our S value and Boltzmann's constant back into the equation to solve for a value of W.